We all know stress. As a chemistry PhD student, this could be a lot of different things for me. Say my experiments aren't really working one day, my PI is coming into the lab to check on us. Fortunately, as a human being, I have a lot of ways to deal with this kind of stress. I can talk to my friends, I can go for a run, I can have a nice warm beverage, I can even just go to sleep. Microbes also know stress. For them, it's things like harsh environments, other microbes even, and limited resources that they need to survive. But what do they do in response to stress? Well, the answer is chemistry. Today, I want to tell a story about microbes, the world's best and smallest chemists. Because microbes do chemistry and build molecules in order to survive stress, humans have often found that these molecules have fantastic activity. One of them that we're probably the most familiar with is penicillin, which I show here on the left. It comes from a mold that we often see growing on oranges. Vancomycin is another really good example, famous in healthcare for treating MRSA. And one that's a little less known is here on the right, mitomycin C, a chemotherapy drug. We were really interested in mitomycin C for this small feature that I've highlighted here in green. So let's zoom in on that. In green, we see something that we call an aziridine. An aziridine is just a small reactive ring of atoms. And so we can see those three atoms are joined by chemical bonds. And chemists like to abbreviate, and so they draw it like this. Here is just a handful of examples of microbially made molecules that contain that aziridine. And as we can see, they have some awesome activity. We see a lot of antibiotics, immunosuppressants, other cancer inhibitors. How the heck are aziridines doing this? Well, aziridines are potent DNA alkylators. What does this mean? Well, we can take a look at a strand of DNA, which I show here on the left. We can toss in an aziridine, and something begins to happen. The DNA starts to stop interacting with each other and start to go after the aziridine. In this way, you'll form a chemical bond with the aziridine, and it'll disrupt the DNA and halt cell growth in tumors. It's an awesome, awesome mechanism. And so when I started my PhD, no one really knew how microbes were doing it. How were they making cancer drugs? We wanted to find that out. And secondly, we wanted to know if we could use microbes to make our own therapeutics. Could we add those aziridines into whatever we wanted? And so for the first part of this talk, I'm just going to address this first question. How do microbes make aziridines? Well, in order to talk about this, we're going to talk about incentives. So here are three children. How do we get the children to hold hands? Now, notice this one on the right, he has a cookie. Kids love cookies. He's not going to want to drop his cookie to hold hands. Now, what if we did some magic and we turned the cookie into a bowling ball? Now when this guy on the left reaches over to hold hands, the guy on the right holding his bowling ball is incentivized to drop it. It's pretty heavy. He doesn't want to keep holding that. So a ring will form, the bowling ball will be tossed, and you'll get your little ring. We can incentivize molecules to do the same thing. So let's get that magic going again and attach a bowling ball to our molecule. Well, in reality, we don't have bowling balls in chemistry. Instead, we're going to call it a sulfate, which is this molecule here at the bottom. But essentially, the same thing can happen. We can have our atoms reach over to hold hands, our sulfate or our bowling ball will fall off, and we'll get our aziridine ring. Now, and microbes don't do magic. They're not out there with wands. They can't perform magical things. Instead, they use something called enzymes. Enzymes are proteins that can perform chemical reactions. Now, what we want to do is find an enzyme, right, that can attach a bowling ball onto things. That sounds easier than it really is. And so this is real data that I've looked at. It looks admittedly a little overwhelming, lots of arrows and colors and things. What does it mean? Well, we can think about an IKEA chair, and we can think about a molecule. Both have instruction manuals. But for a molecule made by a microbe, the instruction manual looks like this, where each arrow represents an enzyme that exists that is inside of a microbe. Now, we can use computer programs and our own intuition to start to read through these instructions. And so what we did is pull out 3 different enzymes from 3 different aziridine-making microbes. And fortunately, in the 21st century, we have the ability to just type these sequences in online. We can order them, and they come in about 2 weeks in the mail. We can bring them into the lab, grow them, and test them. Now, how do we monitor the enzymes once we have them? We use a tool called mass spectrometry. Now, mass spectrometry I always found was a little bit easier than the other chemistry things in order to understand. So here on the right, we have a molecule. When we add up the weight of every single atom in this molecule, we get an exact weight of 141.0096. Now, if we were to put a solution containing this molecule into our mass spec, it will travel through all the different compartments in the mass spec, and the mass spec will spit out a graph that shows a nice, beautiful peak that says 141.0096. There is our molecule. We know it exists. Now, we can do that for our enzyme reactions. The first time I ran this in the lab, I used a little bit of a bigger molecule here on the left. I call it prolanol. And we can monitor for the product, which in this case, we're looking for a 180.0336, which is our molecule with its bowling ball attached. Like any good scientist, we want to do some controls. And so we can take out our enzyme, see if we see anything happening, and we don't, no peak. That makes sense. We can do a similar control where we don't have any starting material, we just have our enzyme, and again, no peak shows up. But when we put the whole thing together, we see this beautiful peak show up, showing that 180.0336, and that's it. That enzyme is putting on our bowling ball. And it turns out that all 3 of our enzymes produce those critical aziridine intermediates. Now, let's return to the second question. Can we use microbes to make our own therapeutics? The answer is we're working on it. Currently, we can use engineered host microbes to do our reactions. We can stick enzymes inside of things like E. coli, freeze dry them, and toss them into reactions. They work beautifully. We've also found that a lot of this has general applicability, so we can test our reaction on a lot of different substrates, and we can start to attach that aziridine intermediate to all of them. And so what I'm doing now is working to install aziridines on a wide variety of molecules in order to make new therapeutics. And so I'd like to finish where I started today. Microbes are the world's best and smallest chemists. They have the tools to make beautiful and life-changing molecules, and it's up to us to find them and harness them. Thank you.